Am I supposed to stand at the podium to speak? Like, is that mic on? It's up to you. You can either use a hand mic or I'm going to hand mic to introduce you. So you can get from the or you can stand here. Yeah, yeah. I think there's one. Oh, you will point. No, it's working. So just start with from okay.
Hello, everyone. It is my pleasure to welcome you all to the second lecture in the Institute Colloquium series. This is a series of lectures designed to foster interdisciplinary dialogue and to allow researchers and the people here at TIFR to engage and access ideas beyond their immediate field of research. We all know one of the great strengths of TIFR is that all the various streams of sciences, physics, chemistry, biology, mathematics, and computer science, they're all happening under the same building, in the same roof. And this series is an attempt to further strengthen this identity of TIFR as a unified institution that covers all the different branches of sciences. The first lecture in the series happened a few months ago, and today we are having the second lecture. The speaker for today, I'm very happy to introduce him. He's Jan Mertz. He's coming to us. He's a researcher in computer science at the Charles University in Prague. And his main research interests are computational complexity, catalytic computing, and space-bounded computation. We all know computational complexity is the study of computation under limited resources. What is the smallest amount of memory that I need to run my program? Catalytic computing is a brand new area of research. It's extremely exciting, and it pushes it to its limit. What is the smallest amount of memory that I need to run my program? Not just that, can I run my program when I have no memory? And this is what we're going to learn about today. Before his current stint at Charles University, he was a PhD student with Tony Pitassi at University of Toronto. Before that, he was an undergrad at Rutgers University. And in between, he has been at the University of Warwick and Kyoto. So he has been to Japan, UK, USA. He's now in India. I talked to him, his next stop is New Zealand. And he's going there to not just do space-bounded computation, but also to do jet-lag-bounded computation. He wants to work in a space restriction and a jet-lag restriction. So the next time he comes here, I'll be happy to have him talk about that. But I know for a fact that he's an extremely nice person, extremely approachable. In case you have any questions, feel free to pester him, annoy him. I want him to be annoyed. I want his time to be occupied. He's with us for the entire week, so feel free to reach out to STCS. I'll be happy to connect. With that said, let us welcome Jan Mertz.
Oh, okay, this works?
Yeah.
All right. Oh yeah, I can hear it actually. Everyone good with this? Yeah, all right, great. Yeah, thank you so much for the introduction, and really it's great to be here. I was here all of last week, so jet lag hopefully not so bad at this exact moment. Although as Raghavan says, next week is going to be potentially quite rough, so we'll see how this goes. But today I'm going to talk to you about computation using a full hard drive. We're going to see what this even means, some kind of crazy tricks for how to use full memory for computation, and along the way we're going to be talking about some of the deepest problems in theoretical computer science, namely the nature and relationship of time and space. Yes, okay, all the physicists have rolled their eyes already. You know, as I said at the lunch, we get more clicks when we say this too. So, and unfortunately, it's not the cool, you know, space-time curvatures kind of time and space. It's regular old runtime and memory. But nevertheless, this is truly one of the deepest problems in the field of computer science. And so, just to orient ourselves briefly, when we're talking about time, we're talking about how fast we can carry out a computation, as measured by, say, the number of cycles that your processor takes to solve a certain problem, some kind of generic measure of time. And in practice, this is probably the most common resource that we care about optimizing. This is something that, like, the runtime of your computation is the first thing you'll notice if you have a bad algorithm. Luckily, there's this idea of Moore's law, which says that every couple of years, computations get twice as fast. This is in fact one reason we measure something like number of processing cycles, because this is a generic thing that carries over no matter how good our hardware gets. This is like a pure measure of how much time something takes. And we do this because then we can ask theoretical questions. And in fact, most of the really big questions that people know of in our field relate to time in some way. So if you've heard of this P versus NP question, this is something about the nature of time. But we can also ask more technical questions like, does randomness speed up your computation if you're allowed it as a resource, etc. A huge variety of questions been discussed since the 1960s and even before. In space, we're talking about memory constraints. We're talking about which problems we can compute when restricted on the number of bits on our hard drive, RAM, etc. we are allowed. And while this is not so common in practice, it's not as widely discussed as time, it is still a very crucial bottleneck in many settings. In particular, in the burgeoning field of quantum computing, every qubit that you use in your machine costs you. Every one of these things is a very hard object to distill down, and so minimizing the amount of quantum stuff that we use is very important. As well as in distributed systems, where the chief time complexity is about communicating between nodes. And thus, doing things locally, the bottleneck ends up being more about space than about minor time concerns. Again, here too, we have a nice little doubling every couple of years or so. There was an idea that we'd hit the wall on this, but now we have these multi-layered chips and all kinds of amazing things. So really, progress continues unabated in the space world. But again, we're going to measure this in some idealized setting where we can ask all kinds of deep questions, in fact, all the same ones as in the time-bounded setting. What's interesting is that those same questions come out with wildly different answers. The state of the art of what we can prove for space is completely orthogonal to what we can prove for time, sometimes for better and sometimes for worse. And this comes back to a number of key differences between time and space. And one of the take-home ones is that time is a resource that once you've used it, it's gone. If I've used a step of time, I can't go back and retrieve it for future use. Whereas, once I'm done with some block of space, I can always just erase it and then use it for a future computation. So this is a pretty fundamental difference between the two. More generically, however, we want to ask, okay, we have time and we have space. Is there a relationship between them? So again, I'm not up on physics. I don't know how this kind of question is discussed. in those settings. For us, there's a very clean way to ask this question. I'm going to define groups of problems. These problems are going to be grouped by when I can solve them, under what resource constraints. And so in particular, I can talk about time t. This is the set of every problem that I can solve in at most t steps. So this is some set of all the functions that I could possibly compute. And likewise, there's a set of functions called space S. Oh, that should be t, sorry. Space t, which is every function which is computable with at most t bits of memory. So a hard drive of at most t bits. And now I can just directly ask, how do these two sets of functions relate to each other? Is one a subset of the other? Are they incomparable? Etc. Turns out we can actually say a number of straightforward things. Any time t computation can touch at most t bits of a hard drive, because every step in time touches at most 1 bit. In particular, just directly, any function which can be solved in time t is solved by the same algorithm in space at most t. And thus, the set of functions computable in space t is at least as big as the set of functions computable in time t. On the flip side, this is an easy little mathematical thing, but if I have space t, so at most t bits of memory, then since there's 2 possibilities for the first bit, 2 possibilities for the second bit, and so on and so forth, the total number of settings of that hard drive is at most, say, 2 to the t settings. And I'm thinking of my hard drive as really containing all the information about my computation, meaning that if I ever see the same state twice, I'm in an infinite loop. Like, the current state tells me exactly how I'm going to proceed from there on out. With this restriction, then it's clear that since I can't go through more than the 2 to the t settings available to me, a space t computation can run in time at most exponential in t, 2 to the t. So we put these 2 facts together, and this gives us some kind of connection between time and space. Space is at least linear in time and at most exponential. We can say one more thing here. If I give you more time, and in particular a lot more time, then provably there are more functions that you can solve. This sounds like an obvious fact, but as we're going to see in this talk, nothing is very obvious in this field. However, I will say that this is true. The upshot of this is that while we have these 2 containments, we also know that one of them is not an equality, but we don't know which one. We know that one of these 2 things must hold in order to satisfy both of these containments and the inequality. Either there are some functions which are computable in space t but require more than t time, or there's a function that's computable in this exponential time, 2 to the t, which requires more than space t. One of those must be true. It's also worth noting that I think most people believe that both of these are true, that neither time t nor time 2 to the t equals space t, but the challenge is to prove this thing. And I think a lot of people who haven't seen complexity or computer science before may not be used to this idea that we can actually prove what's impossible for a computer. And this is really one of the twin pillars of our field. When we work on the theory of computation, the 2 main things we're talking about are algorithms, or what we colloquially call upper bounds, and complexity, also called lower bounds. Algorithms is probably what you immediately think of when you think of computer science. This is studying what we can solve. If you give me a problem to solve and resource constraints, I'm going to apply some cleverness and figure out how to solve this problem under those constraints. Meaning that our chief limitation is just how clever we are at coming up with these algorithms. We can try and try and try, but sometimes it takes a very long time to actually come up with the right solution. However, once we do, there's a good chance that this actually translates to something we can use in practice. You know, everything that your computer runs on is an algorithm. And so this is what we really want to develop for the sake of computation. Complexity, then, is the flip side of this. Complexity studies what is impossible for a computer to solve, what is provably no algorithm could possibly exist to solve a problem under a given resource constraint. Given that impossibility, it's not just about cleverness. You have to disprove every algorithm, not just the ones we have discovered, but anyone that could potentially exist. This is the chief challenge of complexity. And the question is, why would we do this when what we really implement in practice are algorithms? There's a myriad of answers, but the chief one is that it tells us when to stop looking for an algorithm. It tells us that given this constraint and this function, you have no chance of solving this function. And so you're going to have to look for different constraint bounds, different function, etc. And it's worth noting that the field of algorithms is very difficult. Trying to come up with these very clever algorithms for solving things under resource constraints is a tough task that every computer scientist devotes their life to, as opposed to complexity, which is extraordinarily difficult, and we've made almost no progress in 60 years of work. Is a truly abysmal state of affairs on the right-hand side of things. And to give you a sense of why it's so difficult, today we're going to see an approach to proving one of the lower bounds that we just discussed a few slides ago. We're going to show why it fails in spectacular fashion due to a completely counterintuitive style of algorithm. And we're going to see what comes after that. So this is the time versus space problem that I introduced before. We have these two potential lower bounds to prove, either separating time t from space t, or space t from time 2 to the t. And we're going to set our sights on the latter goal. We're going to find some function which is fast, but not space efficient. So this is what we want to show. If you haven't seen it before, the double greater than signs means a lot greater than, the shorthand. This goal was challenged by Cook, McKenzie, Ware, Braverman, and Santhanam in 2012, who gave a function that they conjectured would fit the bill here. That it can take time 2 to the t, but that the space required for it is like quadratic. It's like t squared. And they conjectured this based on the kind of obvious algorithm for solving it, which does take time 2 to the t and takes space t squared. But as we know, you can't just disprove one algorithm. You have to disprove all of them. The reason that they thought that this would work is because there's a good intuition for why the obvious algorithm really does tell you the correct answer with regards to space. So there's intuition for it. Of course, they set out to prove this thing formally, and this is a very monumental task. Even if you could prove it, you would have to show that this obvious algorithm, the structure of it, you could potentially find an algorithm which has the structure of the obvious algorithm, which uses space in a much more clever way. Now, this cleverness seems to contradict what we think of as space, just the baseline laws of space. So really, they kind of said, we need to disprove a bunch of trivial things about the nature of space. And this is a side goal, but if you can achieve both of these, then there's a hope to actually prove that this is the right function to separate time and space. And how do you approach these kinds of things? You build little toy cases, right? You try and solve this for t equals 2, 3, 4, etc. And if I'm being generous, the current state of the art for this is that we've achieved about 3 base cases and done nothing else. I worked on this as a master's student. I'm like half of one of these check marks, and it took me 2 years to even prove anything. So it's a kind of miserable state. And, well, okay, we've made some progress on these trivial facts. Let's try and look at one. So here's one trivial fact. Here are 2 goals. I have a function I want to compute, f. It takes some amount of space to compute, space of f. I don't know what it is, but, there's some space that it takes to compute it. And secondly, I have some string, z, that I want to remember. And again, this takes some amount of space, space z. This is basically the length of z, right? Unless it's a compressible string or whatever, I'm not going to remember this in fewer bits than just the length of it. So those are 2 tasks. And the third task would be to do both at the same time. I'm given a function f that I want to compute and a string z I want to remember, and I ask you, what is the space to do both of these things? So the question is, are these 2 quantities equal? If I sum up the space to compute f and the space to remember z, does that equal the space to do both at the same time? And it seems like the answer is obviously yes. Another way of phrasing the same problem in a slightly different way is consider two scenarios. I give you a small hard drive, or I give you a small hard drive and a much larger hard drive filled with junk that you can use however you want, but you have to leave it as it is at the end. Is there any function that I can solve in the second case that I can't just solve in the first case? This is like an insane question. This is saying, if I gave you a computer and you ran out of memory, that you can solve all of your problems by just plugging in a bunch of full hard drives and somehow get around this. There's just no way that this is possibly true. Unless you've read the abstract or were listening to me earlier, in which case you know actually this trivial fact is completely false. So this was an incredible work by Buhrman, Cleve, Kotsky, Loff, and Spielman who showed that for many of the functions that we actually care about in practice, and for every possible setting of this hard drive, both of these things just fail. The space to compute f and remember z is much less than the sum of these two quantities, and there are many functions for which they could be in low space. We don't know. We're having long-standing open problems, but a very direct approach gets it for you when you're given this full hard drive. Totally crazy fact. Like, no matter how much I see it, I don't fully grasp it. Full memory adds so much power to computation that it's quite unbelievable. And so going back to what we were trying to do earlier, so we have now a hole in our little trivial facts block, which is that one of the things we wanted to prove just doesn't hold. But okay, this doesn't sink the whole approach. Maybe this just means, again, we have to find a workaround. We have to come up with some other structure to the argument, something else that will give us this goal of showing that the function requires some large amount of space. Unfortunately, it just completely falls apart. Using only this fact about reusing memory, myself and James Cook, in a series of work starting in 2020 and culminating just last year, showed that this function that we thought would require tons of space requires very little space. We're not all the way down to space t. It really could still be a separating example, but all of our intuition about this problem is gone. You know, we may as well move on to a different function because we have no real interesting way of arguing about this thing anymore. And in the craziest twist of all of this, earlier this year, Ryan Williams used only this algorithm to show that space t requires way more than time t. From a single function upper bound, he derived an incredibly strong lower bound. Just to give a sense of the irony, we set out to prove the top half of this thing. We instead got an algorithm which gave us the bottom half as the key piece. And in between these two, the key tool is in fact to show that every function which can be computed fast can be computed with so little memory that it's unbelievable. Every time t computation can be recast with space only square root t, with a little factor overhead. It turns out that this is enough to get the lower bound that we're trying on the left-hand side, but this fact alone is probably the most shocking thing to come out of this entire line of work. From a statement about how to reuse full memory, we got something about the nature of time and space. We showed that all time can be simulated with minuscule hard drives. And this is the first real progress on the question of time versus space since the 1970s. An incredibly shocking fact. And I think it brings to light two major things. The first is that from this dichotomy of algorithms and complexity, we actually get a really nice symbiosis, such that complexity tells us to look for algorithms that we would never thought about. This question about how to use full hard drives was never posed in practice until, based on this time versus space thing, we had a reason to show, hey, look, tell me that you can't do anything with a full hard drive. And that was what gave us, in the end, the algorithms that said we could. And then, by some sheer magic, the other way around came about. Given an algorithm, we created from it a result, a no-go result. And so this is a lovely thing about the field of theoretical computer science. There's an interconnection between all kinds of different complexity problems, algorithmic problems, and in fact each other. And the other thing I want to stress, which has already maybe been stressed to death, is that from this dichotomy we had earlier, where time can never be reused, whereas space can be erased and reused, we now understand 50 years later that in fact reuse comes in a myriad of forms and is not some simple, clean thing that we can put our finger on. So we're still learning a lot about the nature of time and space, and this seems to be one major piece of the puzzle. And now, with all of that background and history out of the way, we can finally talk about how do you actually use a full hard drive. I think this is the part that people are most interested in seeing, so we're going to see a few little tricks. I should first set up the model a little bit more formally. I'm not going to really do hard definitions, but I just want you to see what it looks like for us. This was our kind of idealized picture, empty little computer, some full hard disk memory. And when Buhrman and all introduced this, they called it catalytic computing. And in a catalytic computer, you have access to your input, which is whatever you want to solve the function on. You have some space to write the output. And then you have just a little bit of main memory, which you can use however you see fit, completely empty. Think of this as our computer. Plus this catalytic memory, which you should think of as the hard drives. It's much larger than the main memory. You can use it however you want. However, no matter how it is initialized, you have to reset it. That's the restriction of a catalytic computer. And it's called catalytic. I guess the chemistry people are all away for a conference, so oh well. Probably everyone here has seen what a catalyst is. A catalyst is something that can aid a chemical reaction, in fact, enable it to occur in the first place, which is completely preserved by the reaction. All it does is lower the activation energy by creating a new pathway. And here, you should think of these catalysts as being this full memory, which, although it allows this computation to occur, at the end of it, it is exactly as you left it. There are two main techniques that we use in catalytic computing. There's a myriad of small little tricks, specialized algorithms, etc., but there are two main ideas that are a through line throughout it. The first is a compression-based approach, and the second is a reversibility-based approach. And we're going to see those one by one. I'm putting them very vaguely because we're going to put some meat on them in just a moment. So compression is probably the most natural thing to think of. I give you a full hard drive. I say, you've run out of memory, use this thing. Well, of course, the first thing you're going to do is try and compress this. If you can compress it, you've freed up a whole bunch of memory for yourself. You can just do whatever computation you want in the free memory and decompress it later. As I said, we're working in the kind of idealized world where this has to work for every possible setting of your memory. In particular, if it's already compressed as much as it can be, you're not going to get anything out of this, anything useful. And so it seems like you're stuck. Compression doesn't do anything for us. Except that if I try and compress something and fail to do so, what I'm left with is something that's incompressible. And something that's incompressible is very random looking. In complexity, we would say it has high entropy. Again, sorry for the physicists. And this is a useful thing for computation. It's a big open question as to exactly how useful randomness is, but it is definitely the case that as of now, we have many algorithms which work with randomness where we have no idea how to solve it without. And so this gives us a nice dichotomy. Take your catalytic tape, feed it through a compression scheme. This can be one that, in practice, this could be off the shelf. In our theoretical world, we design compression schemes for the task at hand. And of course, if you succeed in compressing, then you have access to more free space, and this is all we really needed anyway to solve whatever we wanted. On the flip side, if we fail to compress, then we're going to utilize the fact that this thing looks random to the compression scheme to run our more interesting randomized algorithms and hope to get some provable guarantees. One important problem for which we can actually do this, instantiate this whole framework, is taking random walks. Now, this is a fundamental problem in a whole bunch of fields, not just theoretical computer science, but in fact in applications, mathematical applications and such, where...
Ian,
yes.
Can you go back to the previous slide? So when you fail to compress,
yes.
why does it become randomized?
So The nature of compression, yes, this is a very good question. So what does compression do? How do you compress something? To compress a string, you have to describe it more succinctly. In particular, you have to record its patterns and the like. You have to write down some succinct description of how that string acts. If a string is not compressible, there are no succinctly representable patterns. There's no way of canonizing the information in that string. The corollary to that is that an incompressible string just has no discernible properties and thus looks very random to any device. There's no device that looks at this thing and can actually tease apart what's doing what. I'm sorry, I should have spelled that out clearly, but this is a very useful dichotomy in theoretical computer science. So, of course, it's only going to be random with respect to this compression. This compression scheme can't tell the difference between this and pure randomness, which in theory, this means we have to design compression algorithms such that anything that fails is good enough for us. This is the key challenge from a theoretical perspective of actually carrying out this framework. In practice, however, just actually running an off-the-shelf compression device should be good. Yes? Say it again? Oh, maybe the mic.
Running of a compression algorithm itself might take some.
Yes, that's the other key. The other key is that this compression scheme itself must work. We must be able to carry it out. So it's not like, we want to do all of this thing in this catalytic computation model, which means our free memory is only a little bit. We actually need to compress using only this little bit of memory. And so we are very limited in terms of which compression schemes we can run. We could think of some idealized compression scheme which always puts a string down to its smallest possible representation. These things don't exist in any practical sense. Like, this is way outside the realm of possibility. But in terms of how we actually use them in the field, we actually cook up compression schemes which do run very, very efficiently. They don't always like, there are some very not random strings where you just don't detect the pattern because you're not using a good compression algorithm. But it turns out that we're always trying to solve functions for which you don't need that much randomness anyway. Or you don't need it to be that pure. It just needs to fit some template. So there's sort of a trade-off with respect to this. Great. So random walks, for our case, let's imagine you have a whole bunch of what we call nodes or vertices connected by edges. And we're going to assume that if I start at some fixed starting place, and I just look at every possible way of walking forward until I can't walk anymore, there's somewhere where I'm going to end up most of the time. Most of the times when I walk from the start, I'm going to end up at the same place. In particular, if I take a random walk, it's going to go there with very high probability. So if I actually got access to like random coin flips and I just used that to take my walk, then I'm going to end up at the same node. If you don't like this 2/3 probability, then imagine doing it a whole bunch of times, right? I take a whole bunch of random walks and I just see on average where I end up. This is going to end up going to the same place with like very, very high probability. So this is a useful task for us to do in practice to figure out how this randomness behaves. And we could say, well, right. I should mention that this is possible to do with randomness and a small hard drive, a small memory. Why a small memory? Because all you really need to do is keep track of where you are currently. If I'm taking a random walk, I don't need to know anything about how I walked so far. I just need to know where I am. And then flip a coin to figure out where to go next. So this is a problem that's solvable with very low memory, plus a whole bunch of randomness. Which means we can hope to just replace the randomness with a full hard drive, right? Just swap them out. Is this going to be good? Really hard to say. There's no guarantees that the walk that's given to us by our hard drive will mimic what an average walk does. But if we do the same thing as before, and we look at what happens if I just like take a whole bunch of walks, you can ask, all right, am I going to end up at the right place most of the time? This is a much more aggregate property. It should work more. But still, I can always just give you a whole bunch of memory that takes you to the wrong place, right? There's nothing that says that my hard drive really takes you to the right node most of the time. The lucky thing about this is that way before catalytic computing existed, Noam Nissan in the 90s had already showed that if I have a whole bunch of walks on a graph and they take me to the wrong place, there's some section of it, and it's not one of the walks, it's going to be some crazy weird section of the tape, which is overwhelmingly, say, 0, or overwhelmingly 1, one of the two. It's heavily biased. If I had a bunch of random walks, on average, they're going to take me to the right place. So if I have a whole bunch of walks which don't take me to the right place, they can't be random. It turns out they're very not random. You can identify a huge amount of the tape which is biased, and a hugely biased string does have some very nice patterns that you can exploit. In particular, it turns out these can be very efficiently compressed to a low memory, at which point you can just use this huge section of the tape you've freed up, do whatever computations you want, and set it back afterwards. So this is the earliest instantiation of the framework. This came from a graduate student in Amsterdam named Yifke de Lek. This is unpublished anywhere, unfortunately. I had to email her supervisor 10 years later to even find the preprint of this, but now this has seen tons of use all over the field with much more difficult compression techniques and solving much harder problems. That's the general framework of how to use compression or randomness.
This part is not saving any space because you just save on randomness, right?
Well, yeah, so saving on randomness. So you're not assuming I have access to any randomness, right? Yeah, I mean, like my catalytic memory is going to be at least as much as the randomness my original algorithm needed. Possibly way more because I need to do this batch, I need a bunch of copies so that I can compress a whole bunch of it. So yeah. Your guarantees aren't going to be quite as good as the amount of randomness. Later results actually do get it a bit tighter. In fact, a lot tighter. All right. The second thing we're going to talk about is approaches based on reversibility. And by reversibility, I mean things that alter the catalytic tape in a way that you can put them back when you're done. And the only real way that I know how to sum this up is it's just magic. Like, everything that you're going to see is how to use arithmetic in ways that are completely unexpected. And the simplest example of this is a technique that every computer scientist gets asked as like an exercise at some point in their undergraduate because it's such a nifty trick. So here's a basic subroutine that we use all the time. I give you 2 blocks of memory, R1 and R2, and they've got some data in them, A and B. And then I want to just swap the memory contents. I want B to end up in R1 and A to end up in R2. Nice and simple. And there's an algorithm that everyone knows from childhood, okay, which is just open up a temporary register. Open up some third little block of memory, store one of your values there for later, then override that value with whatever the other guy has, and move the temporarily stored value up. 3 instructions, very nice, very straightforward. Do it without any more memory. That's the challenge. And I'm going to show you something that works no matter what kind of data you have. To make my life easier, I'm going to treat A and B as just numbers. And the idea is to use arithmetic. Instead of replacing values, I'm going to combine them in some way that I can always get back. So if I set R1 to be R1 minus R2, notice that I haven't lost any information about A, right? If I give you A minus B and I give you B, it's easy to recover A. So even though A minus B doesn't look anything like A or B, you have no notion of what A and B possibly were, I can still recover it. And not only can I recover A, given A minus B and B, I can recover it into either memory location, right? If I add these 2 up, I get back A, and I don't have to add it back in R1. I can just set R2 to be the sum of these 2 things. And given this, I get A minus B plus B, which just gives me A. This has swapped 2 of the values. I now have access to A and A minus B. And again, from these 2 things, I can recover B easily. And so how I'm going to do it, it's R2 minus R1, and I'll just store that value in R1. A minus B gives me B back, and that's my swap. Very cute little puzzle, relying on the fact that arithmetic can always be recovered and can move around however you see fit. And this is our other key trick that we use throughout catalytic computing. When it comes to space-bounded computation, the kind of take-home thing, the thing that everyone uses, the best practice, is whenever you can recompute something instead of storing it, you do so. We don't care about time. We're just trying to optimize space. We don't care if runtimes blow up to oblivion and beyond. The important thing is to recompute whenever we can. And catalytic gives us an even more powerful way to do this. Let's imagine I have a block of catalytic memory. It has some initial value tau. Don't know what it is, doesn't matter. And I have some value x that I can compute and recompute as many times as I see fit. In particular, I can add it. Again, think of this as a number. I can add it to tau. And later on, if I recompute it, I can subtract it back off, get back my catalytic memory, and reset. Great. So now imagine, to see why this is useful, imagine I have a block of catalytic memory as before, and now I have two values that I can compute, x and y. And my goal is to take the product of x and y. Now, of course, normally you would just compute x, store it somewhere, and then compute y, take their product, and we're good. But the only blocks of memory I'm allowing you are this input catalytic block and the place where the output's going to go. So how are you going to do it? Well, we're going to do exactly what we just saw, plus a little bit of cancellation. I add x to tau, have some memory, and now when I read y, I'm going to take its product with this sum. And I'm going to store that in my output. So I get the x plus y term, that is what I really want, plus some junk term, tau y. And of course, this junk term throws off my memory. This looks like nothing useful to me. However, once I reset the catalytic tape, again, by recomputing x, now I have access to tau. And if I recompute y again, take their product and subtract it off, this exactly cancels out the junk term that I didn't want and leaves me with my product xy as I desired, having just computed x and y both twice. This means that I can compute using x, say some arithmetic operations, without ever looking at it. I can only ever adding or subtracting it to memory. I can still utilize it. And souped up versions of this allow me to do this with many, many more values. You can store all of them into catalytic memory. There's a whole bunch of tricks. We've built a hierarchy of computing higher and higher polynomials, and a lot of what we do in catalytic computing relies on making arithmetic versions of computation and then using these kinds of cancellations to get rid of the junk. All right, we're leaving the tricks. So hopefully you have seen something that's piqued your interest, because for the last couple of minutes, we're just going to talk about what can we do and what have we done.
Can you say something about the catalytic memory? It starts with tau. Can you say it's always some linear function of tau or something like that?
Some linear function of tau. Well, the way that I use it here, I guess, right, it's like, I guess you call it multilinear in tau. It doesn't have to be, right? This is not the only arithmetic cancellation instruction in the world. There's all kinds of
Tau sets.
Yeah, what about it?
Yeah, so you change it only to tau plus x. That's you say something like that?
Yeah, that's most of the ways that we use it. But actually sometimes, well, yeah, sometimes we'll multiply it by some constants to get some interesting stuff. But it's easiest to do everything when you're linear in tau. That way you can always just subtract off. You could think about multiplying tau by x and then dividing it later, but now you have to assume that all your numbers are well behaved and everything. So for some applications, it's fine to do much more clever stuff. Great. A quick little history. So this is, I told you Buhrman et al. Introduced catalytic. Here's Buhrman et al. Buhrman, Cleave, Kotsky, Loft, and Spielman. I should mention that Kotsky is actually my postdoc advisor. and that he came and gave a talk on this when this paper first came out. I was an undergraduate. It was the first paper I read. I haven't cared too much about anything since. That's pretty much how this happened. So that was when the catalytic paper was first introduced. There were a couple of things that happened before that of importance. The first is way back in antiquity, there were a couple of results which are foundational in space, and in fact in other fields like cryptography and such. So this first one, this is Barrington, and Barrington's theorem is some touchstone result in space-bounded complexity, as well as a follow-up work by Ben-Or and Cleve. These are not phrased as catalytic. Catalytic wouldn't exist for another 30 years, but they have the key ideas which would eventually turn into the arithmetic reversibility techniques that we saw earlier. That was the first important thing. The second one was to give an inspiration for catalytic. And in particular, it was exactly this whole thing we saw earlier about the attempt to separate time and space. This was done by Cook, Mackenzie, Ware, Braverman, and Santhanam. I should quickly note that Steve Cook was the founder of the P versus NP problem, essentially. Completeness, one of our total stars of the field, has been active from the 60s until now, and this is the last problem that he hung his hat on. He retired in 2019. All of the last decade of his work was trying to show this would happen. But as I said earlier, this trivial fact that they needed to prove along the way is really what inspired the Buhrman et al. Group to look at this idea of using a full hard drive. And so they directly inspired the catalytic results. So after the catalytic result came out, the same authors mostly worked on some follow-up stuff, developing an early theory of catalytic computing, just fleshing out the model and some things that you can say about it, some basic facts. And then to kind of get people interested in the field, one of the authors, Kotsky, wrote a survey about it. Pretty premature because there were only like 4 or 5 results, but still, it did generate a decent amount of interest because over the next 6 years or so, more people got involved. People wrote papers fleshing out the theory, defining even more models, getting more basic results, characterizations, etc. You see a lot more faces here. In fact, you see no one who worked on it before the survey. For some reason, they all stopped working on it around that time, and a whole new crop of people came in. Which, of course, led to another survey, this time by me, and this one was equally premature, even though a lot more had happened. But the reason I chose to write a survey at this point was because alongside this work fleshing out catalytic computing, it also started to see uses in the ordinary space world. The ideas of reusing memory were finally ported to the actual question we care about, which is just what can you solve with restricted memory? Catalytic space be damned. And these works started to really ask that question. In particular, the work by James Cook and myself finally was the one that revisited this first paper, which inspired catalytic, and showed that these catalytic ideas really were enough to sink the whole approach. A funny little thing I should mention about this, as I mentioned, Steve Cook was one of these luminaries of the field. This was his last problem. He put $100 on it. The two of us claimed the $100. I was his master's student, and this is his son. So it felt kind of cheap asking him for $50 for both of us. But nevertheless, it was the hardest $50 I've ever earned, so it was fine. This latter result, in particular, got almost the right answer. Well, we don't know what the right answer is. This is where progress is kind of stalled out, and it was important for 2 things that happened afterwards. The first was this time versus space result by Ryan Williams that I discussed, where he showed a separation between space and time in the opposite direction. Fantastic result. One of the most impactful things to happen in the field of complexity in many, many years. The other thing that happened was that the field completely exploded. So there have been as many papers in the last 18 months on catalytic as there were in the first 10 years of its existence. And not only that, but there's a little gap here. To the left of it is everyone who wrote a paper on it prior to 2024. Over here is everyone who's written on it since. So it's not just that the number of works has come out, but the number of people working on the field has also grown to such a large extent that it's really hard to keep track of everything going on now. I probably missed a few papers here, but nevertheless. And so what can you actually solve? With all this work, what do we know how to do? Here's a couple of functions that are doable with catalytic space, for which we have no idea whether they can be done without it. The first, and probably most important for the general mathematical audience, is the determinant. So the determinant is a very fundamental question. Throughout mathematics, it's some property of a matrix, and it gives us a lot of information about the system that the matrix represents. I should mention these are the techniques we saw earlier, compression and arithmetic reversibility. This one uses just a straightforward arithmetic reversibility argument. We already saw how to do random walks. This goes by the compressor random approach. Again, extremely useful in all kinds of applications. Different from random walks is the question of finding whether two nodes are connected in a graph at all. This is a totally orthogonal question to random walks, because it might be a very isolated vertex. It turns out that using a very different technique based on this reversibility, you can solve this question catalytically as well. And the hardest result, I guess I would say, and a very impactful result in computer science, is that we can compute matchings in graphs. So matchings is the idea that you have a whole bunch of, say, employers and a whole bunch of employees, and you want to pair them up with each other. But it's not like every employer can go to every employee. You have a list of which ones could go together, and you ask, is there a way to pair them up uniquely? Very, again, very useful and fundamental problem. And it seems like it's a bit orthogonal to the rest of these in terms of its complexity. This one actually took a combination of approaches. So both a compression-based approach and an arithmetic approach working in sync to give this result. This is kind of the state of the art for catalytic, although there are many other problems I haven't discussed here of lower complexity. As I said. The other thing is, what implications have we gotten out of catalytic space that work for just the normal model of space-bounded computation? Well, the big one is space versus time. This is the hallmark result from earlier this year. But another useful one is de-randomization. So de-randomization is the idea, like I said earlier, we can compute things like a random walks process given a small hard drive and access to random coins. And a fundamental question in computer science is, can you get rid of the random coins? Is the small hard drive enough to actually simulate your random walks or compute what you want? And this has seen a lot of progress in an orthogonal but brilliant line of work by Ted Pine, Roy Tell, and many other heavy hitters. The problems that I talked about earlier, random walks, connectivity in graphs, we now have algorithms that don't use this arithmetic reversibility or compressor random. They actually use very direct, simple algorithms, the kind that you could teach to first-year undergraduates on a blackboard. Just beautiful algorithms based on this catalytic approach. And an up-and-coming field is to use this in the quantum setting. So as I mentioned earlier, it's very important for near-term quantum computing to not use too many qubits. They're hard resources to procure. They are hard to purify. And so one amazing thing is to use catalytic techniques, when you use catalytic techniques, you don't have to purify your states. You can just use them however they're sitting there with the guarantee that they will be left as you needed later. So this is quantum catalysis has been studied in a very different setting, and it is a frontier of near-term quantum computing. It is now becoming integrated with our approach to find a balance of like what we can and can't execute. Oops, I guess that's my cue to finish.
Yeah.
That's okay. We're at the end anyway. So just as a quick sum up, this work of catalytic computing shows that memory, even when it's being used for storage, it is still a very useful resource for computation at the exact same time, without losing any of its storage properties. This catalytic computing framework is not just a fun piece of trivia, like a little thing to play around with, but in fact is really weighing in on the deepest problems in theoretical computer science. And of course, the big takeaway here is that you really can't assume anything about what is and isn't obvious as to how algorithms can behave, because we're still learning totally new things about the foundations of the field. Quick resources for anyone who wants them. This is from my survey in 2023. I gave a whole bunch of problems to solve. Like I said, field's been active. Like a good third of them are already solved. Still plenty of work left to do. If you actually care about this and you want to see these tricks in action some more, both my survey and the survey of Michal from many years prior, they're equally out of date as to the state of the field, but they're equally good at summing up the nice parts about the field, the techniques, etc. And in terms of keeping techniques up to date, I'm trying to maintain on my website, as soon as I stop traveling so much, I have already some resources on if you want to recap on how these techniques are used, and I have an open problems database in the works to come that will be actively maintained. And so for closing, I just want to say, this is a really amazing field, theoretical computer science. Talking about time and space is what we did today. There's all kinds of questions you can ask. You can ask about logic. You can ask about learning. So, like AI, but in a purely theoretical sense. You can ask about the role of randomness, the strength of parallelism, how things work when you talk about circuitry rather than time or space, correcting errors, and a whole host of other questions. So the field is very vibrant. There's all kinds of questions to ask, and lower bounds are hard, so there's a lot that needs to be solved. So if anyone's interested, please come and work with us. Thanks.
Any questions?
I just wanted to understand your example of multiplication of x, y using the memory tau. So if I understand correctly, so this part was fine. Okay, at this part now you said you have to multiply tau times y and somehow subtract.
Yep.
But where is your tau now? Because earlier you had already calculated. So the second memory that you're showing is the same as the first memory, right?
Yeah, so I mean, I guess I could have already started here and just subtracted tau y like at the start of the computation instead, if that is more comfortable. But the point is that at this point, I've already reset my catalytic tape by computing and then uncomputing x.
So resetting is an operation which...
Yeah, I mean, this is an essential component, right? If I give you a full hard drive and I don't ask for the contents back, there's a very easy algorithm. It involves deleting the whole thing and then just doing whatever you were going to do anyway. So no, it's essential here that we reset stuff. And that's where, and the point of showing this is that you can achieve both goals at the same time. First of all, you can reset, and second of all, you can compute using x without ever seeing it directly. In fact, you can actually, using the same kind of cancellation techniques, and this is a fun exercise, you can do it even when you're like, instead of accessing y directly like this, y also gets added and subtracted to some other block of memory. You can still work out the cancellations to obtain x times y.
I just had to, I just didn't understand, you mentioned that when you are using a compression and it doesn't compress, then the string is random. But isn't the randomness dependent on how you are compressing?
Totally dependent. So, for example, here, what compression scheme were we using for this tape? We could have used any, but actually the one we're going to do is specifically the one that uses this test to identify a biased subsection of the tape and compress it. This is a very tailor-made approach to the problem that we're trying to solve. So the quality of the randomness that you get out, as you say, is dependent on the compression scheme. It will only be as random as you can only assume that it is as random as it takes to fool the compression. However, it turns out that for random walks, you don't need, your randomness doesn't need to be that good. As long as you don't contain any massively biased subsections from some very easy to compute sections of the tape, then you can prove that you get a good estimate when you take an average. That's like the contrapositive of what I wrote here. So in practice, yeah, you need to, again, your compression schemes will not only be tailor-made, but only be able to be implemented on your machines, on this catalytic machine, as I've given it to you. So the whole challenge is to come up with these kinds of compression schemes, which are efficiently computable, but provably good enough to solve the problem at hand.
I want to jump a step ahead. So suppose I give you a harder task. I want to compute a function. You have some catalytic memory, but at the end of it, the memory should also be a function of the original. So let's say it has some other function g, and I want g of tau. Can you say something about that?
Why can't I just compute g first?
I don't want you to spend twice the time. I don't want you to spend.
So this is like also a time-based thing. That's a bit, okay, that's tricky. So obviously when it comes to space, I'm like, the whole paradigm here is that I am willing to pay large overheads in time to optimize the space. So studying fine-grained question about time, how time composes, I would have to think about it. I will say that when it comes to these kind of, these simple walk algorithms here, one of the nice parts about them is that while they use catalytic techniques, they actually recover the time complexity of the best known results. So you actually get, in fact, you can compute like in some way the connectivity of the start node to every node in the graph just in like a linear time. You have to do some work to actually recover whichever answer you want, but it transforms the catalytic tape in such a way that you can recover this answer. So that would be like kind of saving n squared, although again in free memory you can just write everything down. But if you were to do this in like in less space, like log space or something, then these would scale linearly, like for the number of answers that I wanted to obtain. So maybe simple walk algorithms. This paper is actually in particular, this paper down here, Cook-Pine 25, is a good example of this transformation that you're talking about. But I have to think about it more.
Yeah, I was wondering, so far, whenever we talk about machines and stuff, the resources we often keep in mind are the time taken, the time that it requires, the space that it requires. And like you mentioned, there's typically these things that you have that, with more time, we can do more stuff. Should the insight here also be that the amount of full hard drive that you have, should I just think of that as an additional resource, and does that also lead to a hierarchy?
Yes, yeah. So first of all, in the very technical sense that you're thinking of, there is a hierarchy. But in general, yes. There are problems for which now the current state-of-the-art question is how little full hard drive space do I need? How little catalytic space do I need? For the case of random walks, for example, I showed you that you can do it using a list of walks. So some polynomial in the size of the graph space. You can get it down to log squared n, or even log to the 3/2 n. Just full hard drive memory. And of course, now, if you were to reduce this even more, you'd be improving the state of the art for just pure space. So, yeah, those kinds of questions are really important. And they link up to other questions. Like if you can reduce the amount of catalytic space that you need for this matchings question, then you get some novel containments of matching in somewhere in other complexity classes as well. So yeah, the fact that you can do anything with catalytic space at all, any amount of it, is the shocking part, right? Like the weird takeaway here is that full hard drive memory is an extremely powerful resource. And once you've accepted that into your heart, then you can start to ask more fine-grained questions like, well, do I really need that much full hard drive memory? It's possible, by the way, that full hard drives, that space is so powerful that actually it will eventually be able to simulate the power of a full hard drive, right? That actually we're even missing some fundamental techniques about this small little machine. And that all we need is more techniques to show that this can do everything and more. But for now, showing that any amount of catalytic space is enough, and then we can try and drive the parameters down later.
If there are no more questions, let's thank him again.
Please, I will create that
Also, I want to say a couple of things about the upcoming lectures. We have 2 more colloquia scheduled. One of them, the first one is on February. That's from biology, I think. And there's another one in March. So please join us then too.